Welcome back everyone. In the last lecture, we had seen how to find out transfer functions from the differential equations governing a system. Today, we would be looking into finding out transfer functions experimentally. So, sometimes what might happen is that you do not know what the differential equations would be. In that case, how can you find out the transfer function of a system? Or how can you estimate the transfer function of a system? So, for that, I would be showing you an experimental setup, and for that, let us see what is the problem statement that we have with us. So, we want to find out the transfer function of a DC motor if voltage is input and speed is output. Remember, whenever you are asking the question what is the transfer function of a system, you should always first tell what the output is and what the input is. Now, in this case, we have voltage as input and speed as output. And suppose I want to later on, I will use suppose this system for speed control of the motor. Basically, I would like to give a particular voltage as input to the motor, and as a result of that, the speed of the motor should achieve what I desire. So, how do we achieve variable speed in a motor? So, suppose you have a motor of 12 volt and 100 rpm rating, DC motor. It means that it will rotate at 100 rpm when 12 volt is applied across its terminal. So, in this diagram, I am calling those two terminals as M1 and M2. Now, if I change the voltage across these terminals to 6 volt, then the motor will rotate at 50 rpm. These are ideal scenarios. Basically, it might not rotate at 50 rpm, it might be less than or greater than 50 rpm, but that does not mean that it will not rotate. So, when I bring down the voltage, you can see that the speed of the motor is changing. Now, suppose you want to do this automatically, the change of speed you want to do it automatically. So, it is not possible for you to manually every time go and change the voltage settings and change the speed of the motor. So, we need some kind of automation, and that is taken care of by PWM signals. So, we vary the voltage across the terminal using something called pulse width modulation signals. And what are pulse width modulation signals? These are digital square waves with fixed frequency. That means the time period of these waves are fixed, and we vary the T on, the amount of time it has to be on. So, when you change the T on, that is the time for which it is on. So, basically it is a digital square wave which moves from high to low, here high being the amplitude that you want to give, say. Then changing this T on changes the voltage that goes into your DC motor. Now, how much are you changing? So, this is a parameter called duty cycle which tells you the ratio of on time to total period. So, for how much time is the signal on is given by this duty cycle. Now, the average voltage that goes into the motor is given by the supply voltage into the duty cycle. So, if you give a duty cycle of say 50%, that means T on is half of the time period. So, T on is equal to T by 2, say. In that case, it means that the duty cycle will come out to be 50%. If you put the quantities here, so this is T by 2, so T by 2 by T, so half into 100 will give you 50%. So, that means 50%. So, if you give 50% here, so 50% multiplied by, suppose as I explained, suppose the motor was of 12 volt. So, 12 volt multiplied by 50% means that 6 volt will be supplied across the terminals of the motor. So, if you apply a PWM signal of 50% duty cycle, that means 6 volt is being applied across the motor. Similarly, if you apply 75%, then 3 by 4th of 12 will be applied, that means 9 volt will be applied across the motor. So, that means in this way, by changing the T on time or the duty cycle, you can change the voltage across the terminals of the motor, which means you can change the speed of the motor. So, higher the duty cycle, higher is the average voltage, faster the motor speed. So, here is a simulation which shows you when you change the duty cycle. Here you can see I am changing the duty cycle and here the average value is changing. Now, in this case you will see that when the duty cycle is 100%, that means it is on, T on is equal to T, in that case you are getting 1 volt across the motor. Now, of course, in this example I took it as 1 volt, this can be 12 volt also. Okay. So, this is how we change the speed of a motor. Now, in order to ensure that we are giving PWM signals to the motor, so what is used is what is known as an L293D motor driver. Using this motor driver, we feed PWM signals to the motor, and not only that, it also helps you to supply the required amount of current that the motor needs. This, now you see, remember what we are trying to find out. Again, our problem is that we want to find out the transfer function of the DC motor, where output is your speed is your output. So, we are trying to find out the RPM, omega s, which is the speed, and then Vs, which is the input, in this case voltage. So, this is the parameter that we want to find out. So, voltage we will measure using the Arduino, using these terminals, and speed I have to measure using some way, right, speed of the shaft of the motor. Okay. Again I am repeating that you see the input in this case is the voltage across this we will measure with the help of the Arduino board, how much voltage is being fed. Okay. And the speed we will have to measure somehow. So, what we have done is we have taken a DC motor which has an encoder in it. Okay. So, now the encoder pulses helps you to calculate the speed of the motor. I will put references that will help you understand how is the speed calculated using encoder pulses. Now, if you have a motor which does not have an encoder, you have to put some kind of a sensor here that will give you the speed of the motor. So, I can measure the speed of the motor using encoder. I can measure the voltage that is applied across the terminal by tapping into these 2 points using A1 and A3 point of the Arduino, and then using that data we can find out the transfer function of the system. Now, for your reference, since you need to know how the circuits are connected, these are 2 references which you can use. These are generic references. These, like if you search on the websites on Google or any other search engine that you use, you will be able to find out several videos on L293D interfacing, or how to use the encoder to find out the speed of the motor. All this you will be able to find out very easily. But here are 2 websites from which you can go ahead and check this out. Now, what we will do is we will switch to the experimental setup and see how is the transfer function found out using that setup.
Hello everyone. Today we will learn about the transfer function estimation of a DC motor from its time response data. For this experiment, we will be using a DC motor equipped with a magnetic encoder, an L293D motor driver circuit to provide power to the motor, and an Arduino Uno board for the controller. Here is the block diagram representing the connection between the components of our experiment. The Arduino Uno board provides the PWM and directional signals to the L293D driver circuit through digital pins 5, 8 and 10 respectively. The driver circuit then provides the input voltage to the motor terminals based on the duty cycle of the received PWM signal. The terminal voltage of the motor terminals is fed back to the Arduino Uno through analog pins A1 and A3. The encoder pulses from motor encoder channel A and B are also fed back to the Arduino digital pins 2 and 3 for speed calculations. The entire setup shall be operated from the MATLAB Simulink environment. For this, we must install certain support packages in MATLAB which would enable it to interface with the Arduino hardware. We shall start by installing the necessary support packages for Arduino. We'll go to the Add-on Explorer, we'll search for Arduino, and we'll install the support packages shown over here. Then we will open a blank Simulink model. We will go to Apps. Here we require to install the MATLAB support for MinGW. After installing this, we are good to go for modeling. In the library browser, we shall see the support library which we are going to require. Here, we can see the Simulink support package for Arduino. This consists of all the blocks for hardware interface with Arduino. In the common subsection, we can see the analog input block. This block reads the assigned analog pin from the Arduino hardware. It will be used for voltage measurement. We can see the L293D DC motor block. This block takes an input ranging from -100 to 100 and generates a PWM signal and direction signals for the motor at the assigned digital pins of the Arduino. In the sensors subsection, we can see the encoder block, which will give us the encoder count of the DC motor by reading the assigned digital pins of the Arduino. We will take a step block, which will determine the duty cycle, and a gain block with a value of 100. Now, the encoder pulse count must be converted to speed. So to do that, we need to make a speed calculation block over here. We'll take a subsystem and rename it as speed calculation. We will go inside the subsystem and start modeling our speed calculation block. We will take an add block, then we will convert this to plus minus so that we can get a subtract operation. Now we are going to find the difference between the current pulse count and the pulse count before one sampling time. We will take a delay block and change the delay length to 1. This will give us the difference between the current pulse count and the pulse count before one sampling time. We will take a gain block and multiply the difference with the sampling frequency, which is 20 in our case. This will give us the pulse per second, which is the PPS. We are going to divide the PPS by pulse per revolution, PPR, which is 2160 in our case. This will give us a revolution per second, and we will multiply this value with 60 to get the speed in RPM. We'll change the sampling time to 0.05. Now, to plot the speed properly, we will take a goto block, we will connect it, and we shall rename the variable as output. Moving on to the voltage measurement part, we are going to measure the voltage between the motor terminals. So we will take another subsystem, rename it as voltage measurement, and we'll start making our voltage measurement block. We'll take two analog input blocks, one for each motor terminal M1 and M2. The Arduino analog pins give us the data in int16 format, which cannot provide negative values. We are going to convert this data type to double for proper voltage calculation. So we take the data type conversion block and we shall convert the data type to double. The net voltage that the motor is going to receive will be the difference between the voltage which we see at terminal M1 and M2 respectively. So we are going to take the difference of the two readings. The Arduino analog pins gives us the readings in the range of 0 to 1023, where 0 represents 0 volts and 1023 represents the maximum voltage, which is 10 in our case. We'll take a gain block and assign 10 by 1023 as its value. So whatever net value we get gets converted to the corresponding voltage. Our voltage measurement block is ready. Now we'll take another goto block and we shall name this variable as input. Now our input and output blocks are ready. We will assign the pin numbers to the analog read blocks. In our case, it is pin 3 for terminal M1 and pin 1 for terminal M2. We'll take a scope and connect the input and output together so that we can compare the results. Our Simulink modeling is done. Now we shall move to the hardware implementation part. For the interfacing, first we'll go to model configuration, go to hardware implementation and select the hardware board. In our case, it is Arduino Uno. Now we'll get this option of hardware board settings. We'll select host port connections. We'll select manually specify and specify the COM port in which the Arduino Uno is connected. To determine the COM port number, we will go to device manager, go to ports, and we can see the COM port in which the Arduino is connected. In our case, it is COM port 7. So we will put 7 over here. Now we will see this hardware panel over here. We'll select the run on board external mode and we'll see this part over here. We shall click monitor and tune, and this entire Simulink model will be compiled into a C code and transferred to the Arduino for running. The DC motor we are using is rated for 12 volt and 130 RPM. We can see the Arduino Uno and the driver circuit over here. On the scope, we can see the input plot and the output plot. The input provided is around 10 volts and the output we can see is around 108 RPM. This is the time response of the DC motor. Now, we will go to the workspace. and we can see that the simulation data is logged over here in the time series dataset logs out. So we have a code which extracts the input and the output data from the log and use the data to estimate the transfer function of the DC motor. Here we can see the estimated transfer function. We can see the Bode plot of the estimated transfer function, and we can see the step response of the estimated transfer function. Now, we have to verify whether our estimated transfer function does correctly represent the system or not. We will take a blank Simulink model and we shall take the transfer function block over here. We'll get a step input and a scope to check the output. We'll put the numerator and the denominator coefficient values of the estimated transfer function in the transfer function block. Now, we will compare the input and the output similarly like we have done in the experiment. Before running, we must set the step value as 10 because we want to compare the results with the hardware data. After running the model, we can see the result looks quite similar. I'll show you the estimated transfer function response and the motor response side by side. So this is the motor response. Let us see side by side so we can do a comparison. Here we can see that both the motor hardware and the transfer function gives quite similar responses for the same input.
You have now seen how to find out the transfer function of a system experimentally. We have used two functions at the end, which was the Bode plot function, Bode function, and the step function. We will learn about those functions as we go along the course, so don't get worried about those two functions. You will soon see what are the meaning of those functions in the upcoming lectures. So for today, I will end it here. Thank you.